Okay, so imagine for a second you're 5 years old.
Okay.
You're in a classroom in northern France, but all the desks,
Mm-hmm.
they're just gone.
Gone.
In their place, there's this massive grid taped to the floor. Huge.
Like a giant game board.
Exactly.
Yeah.
3 meters long, 2 meters wide.
Yeah.
You're standing on one of the squares, and your teacher looks at you and says, okay,
Hmm.
you are now a robot.
It sounds like a game, Fun little afternoon activity.
It does, but then the teacher says, you have to execute an algorithm.
Hmm.
And suddenly, this isn't just hopscotch. This is like a rigorous scientific battleground.
It really is. What you're describing is the setup for a huge research project that ran from 2016 to 2019. They took 230 kindergartners, kids who can, barely tie their shoes.
Right.
And they tried to answer a question that, honestly, I think most adults struggle with. How does our brain actually bridge that gap between the physical world and abstract logic?
We are diving deep today into this Bluebot project, and I want to flag something right at the top because I know what you're thinking. You're thinking, oh, a deep dive on teaching kids to code. Cute.
Right. But this isn't really about coding. I mean, it is, but the coding is just the vehicle. This is really about cognitive architecture. It's about how we learn systems.
And the source material we have is this dense academic paper with a title that practically scares you off. Hypothèse de la distance appliquée à la robot pédagogie.
The distance hypothesis applied to robot pedagogy. It doesn't exactly roll off the tongue.
Not at all. But don't let the title fool you. The data inside is wild. It basically presents a paradox where the methods that should have worked, they failed miserably.
And the methods that look like a total disaster on their own ended up being the magic bullet when you put them together.
It completely upends that whole narrative we have about digital natives.
Oh, yeah. The idea that because a kid is born in 2020, they just intuitively get digital logic, this study basically says no, they absolutely do not.
So we are going to unpack that failure because the numbers are staggering. But first, let's just set the stage. What was the actual mission here?
The mission was to teach computational thinking to 5-year-olds. So algorithms, sequential logic, planning a path. And the researchers wanted to figure out which tool actually works.
So they set up a kind of cage match. 3 contenders.
3 modalities, yes. So contender number 1 is the body. This is what you open with. The child is the robot. They physically walk on that giant floor grid.
Embodied cognition. You use your muscles to learn.
Exactly. Then contender number 2 is the robot. This is a specific toy, a blue bot. It's a little plastic bug, maybe the size of your hand, with buttons on its back.
Okay.
The kid presses forward, forward, left, and the little bug actually drives across a mat on a table.
So physical, but it's external. You're controlling it. You're not it.
Right. And finally, contender number 3, the tablet. A standard 10-inch touchscreen. The child just drags and drops icons to move a virtual robot.
Okay. Body, robot, tablet. If I stopped 100 people on the street and asked which one a modern 5-year-old would master fastest,
They'd all say the tablet.
99 of them, for sure. It seems so obvious, right? It's the cleanest interface.
But science doesn't really care what seems obvious. The researchers split these 230 kids into groups. Some just did body, some just robot, some just tablet, and some did combinations.
And they had a control group, right?
Oh yeah, placebo group. They did nothing, just to make sure the other kids weren't just getting smarter because 6 weeks had passed.
Which is important. We need to know the teaching actually worked. And, spoiler alert, it did. All the training groups beat the placebo group. But when we look at the individual tools, it's a bloodbath.
It really is. So let's start with the tablet, the one we all assumed would be the easy winner.
Give me the number.
The tablet-only group had a success rate of 7%.
7. Just 7%.
7.
That's statistically negligible. That is basically 0.
It's essentially total failure. And to be clear, the final test was on paper. They had to draw the path. The tablet kids could move the icons on the screen, but they couldn't transfer that logic to paper.
The learning didn't stick.
Not at all.
Okay, so the screen is a disaster. What about the physical toy, the little robot?
Better, but not by much. A 14% success rate.
Still a failing grade.
Mm.
And the body, the one where they walk on the floor.
The body method was actually the quote-unquote best of the solo acts. It got around 15%.
So 7%, 14%, 15%. Essentially, if you use only one tool, you're failing, what, 85% of your class?
Correct. None of them work well in isolation.
And this is where the paradox kicks in. Because they tested combinations. And normal linear logic would say you combine your best methods to get the best result.
You'd take your strongest ingredients, right? So you'd think combining body at 15% and robot at 14% would be the winner.
But it wasn't.
Nope. The body plus robot group scored 26%. Better, but, not great.
Okay, so what was the winner?
The winner, by a massive margin, was the robot plus tablet group.
Wait,
Yeah.
you're telling me they took the 14% method and the 7% method, the two biggest losers, and combined them.
And the success rate just shot up to 39%. It was the highest score in the entire study.
That makes absolutely no mathematical sense. How do two negatives make a positive? Why did the two worst tools create the best outcome?
That is the million-dollar question. And to answer it, we have to stop thinking about tools and interfaces and start thinking about cognitive distance.
This is the distance hypothesis from the paper's title.
Exactly. It's based on work by a researcher named Greff. The idea is pretty simple. Learning gets harder the bigger the gap is between your physical reality and what you're trying to manipulate.
Okay, but distance usually means like meters or feet. You're talking about something else here.
I'm talking about cognitive load. The researchers break distance down into different axes. There's spatial distance, sure, but there's also sensory distance.
Let's apply this to the body method first, because that's the one that confuses me. You said it was the best of the single methods. It's zero distance, right?
Yeah,
You are the robot.
it should be.
So why did it fail to get high scores? And why did it perform so poorly with the robot?
We assume being the robot is easy because it's embodied, but we're forgetting one huge factor: scale.
Her scale.
Think about the setup again. That grid is 3 meters long.
Right.
Now, picture a 5-year-old. How tall are they?
I don't know, a meter. Maybe 1.10 meters.
Exactly. So imagine you are 1 meter tall, standing in the middle of a map that is 3 times bigger than you are. What do you see when you look down?
I see the floor. I see the square I'm on. Maybe the edge is the one next to me.
Right. You're immersed in the landscape, but you can't see the structure of the landscape. You can't see the pattern.
It's like being in a corn maze versus looking at the maze from a helicopter.
Precisely. The technical term they use for this is anamorphosis.
Anamorphosis. That's a great word.
It just means a distorted projection. When the child is inside the grid looks warped to them. The teacher, an adult, is standing up and looking down thinking, this is so obvious, just go forward 2 squares.
But the child can't see 2 squares forward as a concept. It's just an endless expanse of floor tiles.
Their cognitive load isn't how do I code, it's where am I? What is this giant shape? They lack what the researchers call the plan view.
The big picture.
Yeah. And there was this fascinating anecdote in the notes where one teacher realized this was happening. She actually let the kids stand at the top of a staircase and look down at the gym floor.
Oh, that's brilliant.
And suddenly the kids all went, oh, it's a grid.
Because they finally got the plan view.
Right. But in the controlled experiment, they had to be on the ground. So the body method, while fun, introduced this massive cognitive distraction. It was spatial confusion.
So it's noise, not signal.
Exactly. And that explains why it didn't pair well with the robot. If you start with the body, you're not teaching logic, you're just confusing the kid with perspective.
Okay, so that explains the body failure. It was too big. Now let's go to the tablet failure. 7%. That one really shocks me because the screen is small. You can see the whole thing. You have the plan view. Why did it fail so hard?
This is the opposite problem. The scale is fine, but the sensory experience is hollow. The researchers call it the isomorphism trap.
Isomorphism. Okay, break that down for me.
It means same form. The tablet game looked exactly like the paper test they took at the end. Same icons, same grid, same little character.
So logic says you practice on the thing that looks like the test. You should ace the test.
But looks aren't everything. The problem is what they call the haptic gap.
Haptic meaning touch.
Yes. On a tablet, it's all smooth glass. You drag an icon, there's no friction, no weight. The child moves a virtual robot, but their brain hasn't built a model for what that movement means in the real world.
It's just pixels changing color.
It's a ghost. The researchers argue that for a 5-year-old, this is remote distance. Even though it's right in front of their face, it's cognitively very far away because it doesn't engage their sensorimotor system.
They aren't feeling the forwardness of moving forward.
Exactly. They're just sliding a finger on glass. The concept doesn't stick because there's no physical anchor.
So we have the body method, which is too immersive and confusing, and the tablet, which is too abstract and slippery. This brings us to the hero of the story, the robot, the blue bot. Why was this the magic ingredient?
The robot is the Goldilocks solution. Look at the dimensions first. The mat is on a table. It's about 1 meter by 60 centimeters.
So the child can see the whole thing at once.
Yes, they have the plan view without needing to climb a staircase. No anamorphosis.
Okay, so it solves the body problem.
But, and this is key, it's also physically real. The robot is a chunky piece of plastic. You have to push down hard on the buttons. It physically crawls across the table. It bumps into things.
So it solves the ghost problem of the tablet.
Precisely. It anchors the abstract idea of an algorithm into a physical object that you can see and touch in its entirety.
So now we can finally solve the paradox. Why was robot plus tablet the super combo? Because individually, the robot wasn't that great. Only 14%.
Right. Individually, the robot is good for understanding the movement, but maybe not for the repetition you need to really memorize the logic. And that's where the synergy comes in. It's all about scaffolding.
Scaffolding. Building a structure to hold the learning up.
The researchers believe the robot phase builds the mental model. The child plays with the physical toy. They learn, if I press this, the object moves there. They lock that in. They build the neural pathway using the toy.
They get the physics of it.
Right. And once that pathway is built, once the brain understands the logic, then and only then can they switch to the tablet.
And suddenly the tablet isn't a ghost anymore.
Exactly. Now, when they see the virtual robot, their brain says, oh, I know what this is. This is just a picture of the blue bot. They project the physical reality they learned onto the screen.
The tablet becomes a tool for generalization.
Yes. It lets them practice the logic quickly, over and over, without having to reset a physical toy. But it only works if the robot did the heavy lifting first.
That is such a powerful insight. You can't learn the symbol until you've learned the object the symbol represents.
You can't learn the map until you've walked the territory, or at least played with a miniature version of it.
It reminds me of how we learn almost anything. You don't learn to drive by playing a video game. You need the feedback of the wheel. But once you know how to drive, a simulator can help you get better.
That's a perfect analogy. The tablet is a simulator, but a simulator is useless if you don't know what you're simulating.
So based on all this, the researchers actually proposed a specific sequence for teachers. They didn't say burn the tablet.
No, they see value in all of them, but the order is non-negotiable. Step 1, body.
Wait, even though it was confusing and had the perspective issue.
Yes, but for a different reason. It's emotional, it's engaging, it gets the wiggles out, it gets the kids interested in the idea of moving. But the teacher has to know they aren't learning the coding logic yet.
So step 1 is just engagement. Step 2.
Step 2 is the robot. This is the learning phase. This is where the actual cognitive work happens. You use the physical toy to cement the concepts of forward-left sequence.
And step 3.
The tablet. Once the concept is mastered, you move to the screen to reinforce it. The screen is for application, not for discovery.
That distinction, discovery versus application, that's huge. I feel like in a lot of educational tech, we try to use the screen for discovery.
And this study suggests that's just a mistake. The screen is efficient, sure, but it's poor at building that initial mental scaffold.
There's also a mention of Gardner's multiple intelligences in the research. How does that fit in?
It just validates using all three. Look, some kids are kinesthetic, they need the body face to even care. Some are logical, they'll click with the robot immediately. By cycling through all three, you cast the widest net.
You give every brain type a chance to hook onto the concept.
Exactly. But the critical path, the one that ensures success, always seems to run through that physical object. The robot is the bridge. You can't skip the bridge.
This makes me wonder about us as adults. We're always trying to learn new abstract things. AI, cryptocurrency, complex software.
Yeah.
And we almost always try to learn them through screens.
We do. We watch a video, click through a tutorial.
Maybe we're making the same mistake. Maybe we need a blue bot for understanding the blockchain, something we can touch.
I think the broader lesson is about that plan view. When you're learning something complex, are you stuck in the body view? Are you so down in the weeds that you can't see the pattern?
Or are you suffering from that anamorphosis? You're looking at the data, but it's distorted because you don't have the right perspective.
Sometimes you need to step back or stand on a chair to see the structure. That's what the blue bot did. It took a 3-meter problem and made it a 1-meter problem.
It compressed the problem to a manageable size.
That's what good teaching is.
So to wrap this up, effectiveness isn't about the newest technology. The tablet was the newest tech in the room, and it was the worst performer by itself.
Right. We are physical beings first, digital beings second. The brain has to grasp the physical before it can project into the virtual.
That 93% failure rate on the tablet alone is going to stick with me. It's just a stark reminder that just because a tool is modern or clean doesn't mean it works.
And that efficiency isn't about speed. The robot method takes time. You have to lay out the mats, charge the batteries. The tablet is instant. But the slow method created the structure that made the fast method work.
We have to go slow to go fast.
In learning, almost always.
This has been a really fascinating look into how we think. It's easy to dismiss a study about 5-year-olds as child's play, but the cognitive architecture is the same.
Absolutely. The fundamentals don't change just because we get taller.
A huge thank you to Quentin Alvarez and his team for doing the hard work of watching 235-year-olds.
That is a lot of patience.
And thank you for helping us break down this distance hypothesis.
My pleasure.
To everyone listening, the next time you feel lost in a new topic, ask yourself, do I have the plan view? Or am I just wandering around on the tiles? Maybe you need to find your own version of the blue bot.
Or just stand on a chair.
Always good advice. Thanks for diving in with us. We'll see you on the next one.